Alright, hello and welcome everyone to the section of video in which I am explaining about the process of elongation in the DNA replication in the eukaryotes. In my first video, I explained about the process of initiation in the DNA replication in the eukaryotes. So, if you have problem in understanding this, then you can please go and watch my previous video. Now, coming to the part of elongation, in the process of elongation, the first enzyme we required is helicase, and the helicase enzyme is made by the helicase complex is made by three enzymes, namely NCM protein, GIN protein, and CDC45. They work with one another and they act as a helicase complex. Now, another difference between the prokaryote, this is the first difference. The helicase complex itself is the different thing in that is different in prokaryotes and different in eukaryotes. And another difference is the synthesis of leading strand in the eukaryotes is taken place by the DNA polymerase epsilon, and the synthesis of the lagging strand in the eukaryotic DNA replication is taken place by the is done by the DNA polymerase delta. And another difference between prokaryotic and eukaryotic elongation is this part. The primase enzyme in case of the elongation is DNA polymerase alpha. DNA polymerase alpha is acting as a primase enzyme which is annealing the small short strand of 10 to 20 nucleotides of the primer. Now, another thing. Alright, now let's go to the process of replication. Now, what happens is first the primer will anneal the short stretch of the DNA to the 5' end, and the DNA polymerase epsilon will start to make the new strand of the DNA, and the helicase will unwind the DNA. This is done. Now coming to the lagging strand, because every time we know that the synthesis of lagging strand is much difficult task as compared to that of the leading strand. So in lagging strand, alright, one more thing, this is pCNA ring, and this pCNA ring is helping to hold the DNA polymerase, because DNA polymerase is heavier in molecular weight as compared to the DNA strand, so it will be not attaching properly to the DNA strand, or it can fall off. Alright, so this pCNA is making sure that the DNA polymerase is holding the DNA. Alright, now okay, I was in the lagging strand, and another thing is, yes, there is a SSB protein. SSB protein means single stranded binding protein, which is just helping the unwinded DNA to not unite or not form a bond again. Alright, because the single stranded DNA, they are sticky in nature, and then if the helicase is walking and unwinding the DNA, it has a probability to make a bond again. Alright, and another thing is, it is also very susceptible to the nuclease activity. It can be destroyed by the nuclease enzyme. So to protect them also, the SSB protein, namely replication protein A, is binded to the single stranded DNA. In case of the leading strand, much of the SSB protein is not required, because the synthesis happens as soon as the helicase will unwind, the synthesis will occur. Helicase is unwinding, the synthesis is occurring. But in case of lagging strand, SSB protein is playing a major role, because the lagging strand synthesis is delayed quite a lot, because it needs to turn in order to come to the same direction, right, in which it is walking. This is walking in this direction, and it need to turn to come in to help the polymerase to walk in the same direction, right, to bring the directionality of the polymerase enzyme. The lagging strand synthesis is taking place in a slow rate. If there is synthesis of 1000 to 2000 nucleotide, then only the synthesis of the lagging strand is beginning. Because see, we can see that this place is getting synthesized, but we can see that this place is vacant. Why? Because this is getting unwinded, this is coming, this is turning and turning, but this place is vacant. So this place need to be always covered by the SSB protein, right? Alright. Now what happens? Every time this will come and turn, every time what happens? The primase, DNA polymerase alpha is need to anneal the primer. Let's make here. Alright, now for example, this polymerase has shifted here. Alright, this is this. Now we will add another primer here. Now let's make this strand has shifted here. Alright, this has shifted here. Now new strand, again another primer. Again now this strand has shifted here, for example, and this is the new strand, and again another primer. In this way, the 5' to 3' primer is added at every point. Alright, to make the directionality of the enzyme favorable. Alright, it is only added one time, but in case of a lagging strand, it is added in the form of the patches every time. Alright, to bring out the directionality of the polymerase enzyme. We can see that the synthesis, it is happening in this direction, and here also the synthesis is happening in this direction, so that it will become easy for the polymerase to act. Then for bringing this thing in this direction, alright, for 5' to 3' direction, what thing that lagging strand is paying to bring the synthesis in the 5' to 3' strand? That is, it is turning itself. Alright, it is turning itself, and then the primer is annealing every time over here, and then it is synthesizing. Again it is turning, and again primer is adding, and it is going. Again it is turning, again primer is adding, and it is going, and it is finally forming this kind of structure. This kind of structure. Alright, and then this is RNA primer, and this is newly synthesized DNA strand. Right? This is the RNA primer, and this is the newly synthesized DNA strand. Then what happens is this part. Alright, now let us take this part. Now the leading strand synthesis is easy, it is okay. Now the new strand which has formed in the leading strand is whole the DNA. But the lagging strand, how to make the whole of the lagging strand a DNA strand? Because there are the RNA patches in between them, right? So to make them a DNA strand, another protein known as FEN, F-E-N and DNA pol delta. The same DNA pol delta and FEN, they remove this primer. Alright, they remove this primer, and in the course of removing this primer, what they do is they will remove some of the nucleotide also. Alright, some of the nucleotide also, and this primer will be forming a flat kind of structure. They will remove a primer, and in that course they will remove some of the nucleotide. Not primer will be removed, but some part of the nucleotide will be in the form of flap. Flap means it can open and close. Alright, means this is flap. This can close and this can open, right? It is kind of flap. It will form a flap. Now this can close also, right? It will form a flap kind of structure. Here also, while removing it will remove the primer, but it will remove some stretch of nucleotide also, the DNA, and it will form a flap. Alright. So, it will form a flap. And now, what happens is, see, the another enzyme known as DNA2, the another enzyme known as DNA2 is having both the helicase as well as the ligase activity. Alright, so what it will do is, with the help of the helicase activity, it will remove the flap. With the help of the helicase, this DNA2 is having both the helicase as well as ligase activity, and with the help of helicase activity, it will remove this flap. And with the help of the primase activity, what it will, with the help of ligase activity, it will seal the gap. It will fill up the gap. Alright. And this was only for the process of initiation. I hope you got to what I explained, and I hope you enjoyed watching it. If you liked my video, just hit the like button and subscribe to my channel, and wait for the more exciting videos. Thank you.